What's up, nerds? Let's learn about imaginary numbers. So, before we learn about what an imaginary number is, I want to do a little investigation to figure out why we need something that's imaginary and why we call it imaginary. So, this first example wants us to consider a quadratic function, and we're going to find the solutions algebraically. So remember solutions, another word for solutions is zeros. So we can set that equation equal to 0 and solve. Subtract 1 from both sides. Take the positive or negative square root. And we get a situation that we've seen before. We get the square root of a negative, which we know means there are no real solutions because our calculator tells us that we end up with a non-real answer. So what does that mean? That means that graphically, when we look at this function, we know that plus 1 means it's going to be the quadratic parent function shifted up 1. We end up with no x-intercepts, right? So we can't see anywhere where it crosses the x-axis or even touches the x-axis. So visually, that's what no real solutions means. But let's look more at that error that the calculator gives us. So the calculator gives us an error of non-real answer. Okay, and if we investigate this word non-real, if you think of a synonym for something that's not real, hopefully you may think of the word imaginary. And the reason that we say, or your calculator says it's a non-real answer, is because we are used to working within the real number system, right? In chapter 0, we talked about irrational and rational numbers, which are both examples of real numbers. And I said that eventually we would expand that number system. And that's what we're going to do today. We're going to expand it to non-real answers. And just the best word that we have, instead of having to say non-real all the time, is imaginary. So that's why we call them imaginary numbers, even though they do exist. They do have a place in the real world. But for us, again, it maybe is a poor name because it makes it seem like it's made up and it doesn't exist, but they do. We are going to define the imaginary unit I as the square root of -1. And what that allows us to do is expand our number system to now allow us to take the square root of negative numbers. And we can do that by using that multiplication property of radicals. So then looking at example 2 here, we can use that multiplication property to split this up into the square root of 9, which I know is a perfect square, and I can do that because that is a real number. And separately, I can take the square root of -1. And remember, we know that two things without an operation between, the implication is that I'm multiplying them. So this would simplify down to 3, and we just defined the square root of -1 to be our imaginary unit I. So we have just created our first imaginary solution, right? So our imaginary number is 3i. Okay, we can try b, right? B is another perfect square, so I'm going to split that into its real perfect square part and that imaginary unit, and that is going to simplify to 14i. Remember, I do not have a plus or minus here because the square root was already there. Okay, C is not a perfect square, but I can go ahead and split it into, in this case, I'm going to split it into 3 separate parts. I'm going to split it into its real perfect square part, the imaginary unit, and that irrational number that is simplified and just kind of left over. Okay, so square root of 16 is 4. I have my imaginary unit I and the square root of 2. So this is typically how I style this answer. However, it is also very acceptable to write this. However, we need to be really careful. Okay, the better way to write what I just did is to put the coefficient in parentheses. And the reason is because not all of us have nice, neat, perfect handwriting. And if you are a little bit sloppy and wrote the answer like this, I would mark it wrong because you have very unclear communication in this answer. I cannot tell from this answer, is the I supposed to be underneath the square root, or are the two supposed to be completely separate? Right? And in order to emphasize my point, I put a multiplication sign between the square root of 2 and the I. So that way we can very much tell they are two separate pieces. This is very unclear in the communication piece. So there's a couple things we can do to avoid a miscommunication. One is to put a time sign in between the two terms, or really the two pieces of that term. One is to go ahead and put parentheses around that real coefficient. And the other is the way that I did it originally, which is to just put the square root at the end. So that way I don't risk anything looking like it's underneath the radical other than just the argument or what I intended to be the argument itself. So that's something that's really important for you to keep in mind, is very clear communication of what you intended the answer to be, especially if you don't have nice, neat, perfect handwriting. Okay, and on the clear communication piece, I did not clearly communicate the directions for example 3. I accidentally said to simplify each expression, but not a single one of these is an expression. I meant for the directions to be solve each equation. And to solve each equation, we need to isolate x. So I'm going to go ahead and move 81 over to the other side by subtracting it from both sides. I can take the positive and negative square root of both sides. I can go ahead and split this into its perfect square real part and its imaginary unit. And then I can simplify that. Positive or negative 9i. And notice that this communicates two different solutions. The two solutions to this quadratic are positive 9i and negative 9i. Alrighty. Example B here, we can subtract 8 from both sides. I'm so sorry, I was thinking about what the solution was going to be. We're going to subtract 9 from both sides. We get negative 8. Divide both sides by 2. Take the positive or negative square root. And notice that I do a lot of steps in my head, right? I subtracted 9 from both sides in my head. I divided by 2 in my head. But I always write this step out because I have learned that if I don't write this step out, then I often forget to put the positive or negative sign with my solution. So that's part of the important part of practicing, is that you learn where you make mistakes and what you can do to ensure that you don't make them on tests and important assignments in the future. Okay, another thing you can do, right? I simplified the square root of negative 4 in my head because I can tell that that is a perfect square with an imaginary component to it, or an imaginary part. Okay, I suggest go ahead and pause the video here. You can skip ahead and check your answers and then just come double check them. More than welcome to listen to my spiel if you miss any of them, but I bet you can move on and feel pretty solid about the rest of these on your own. Alrighty, I know the square root of 6 is not going to simplify, but we can pull out that imaginary part. And remember, if we wanted to, we could put the coefficient in front, but I just want to include parentheses for that clear communication piece. Okay, on D, we're going to subtract 13 from both sides. Positive or negative square root. Okay, I'm going to go, I don't want to simplify too much in my head because again, that's where I make mistakes. but I am going to go ahead and split that up. And you don't have to write both of these answers every single time. I just want to get you to get used to seeing it both ways and also make a really big deal about communicating clearly your answer. And not just clearly, but correctly communicating. Divide both sides by 3. Positive or negative square root, and I don't have my calculator on me. So I'm going to guess. I'm going to do some side work to check, but I feel like the perfect square that's in 147 is probably 49. And I'm going to guess 49 times 3 because I can see that the last digit there is a 7. And I know that 9 times 3 here is also going to end in a 7. So I feel like this is a pretty good guess for the perfect square factor of 147. So look at that. That was lucky. Well, not just lucky. I was using some number sense there to make my life a little easier. So I'm going to go ahead and split that up into negative 49 and 3. Or you can also put the plus or minus sign in front of the square root. That's also totally fine and would be considered clear and correct communication as well. It's got to be there. You can't forget it because there are 2 separate solutions. If you don't put it, it looks like it's only the positive solution. Alrighty, and F. Add 1 to both sides. Okay, this is another part that I don't like doing in my head. I know I make mistakes here, so I'm going to make sure to write it down. 18 divided by 2 is 9. 9 times negative 3 is negative 27. I know that that is... which means my solution's going to be... I'm just going to write 1 because I'm kind of out of room. So positive or negative 3i times the square root of 3. Alrighty. So hopefully you got all those. We're feeling good about simplifying with imaginary numbers now. That's exciting. We've expanded our number system. Let's go ahead and look at something that is going to be really handy for simplifying large powers of I quickly, which is a skill that happens commonly on the ACT. So, powers of I. We have already defined I to be the square root of negative 1. And I know this first example is going to seem a little bit circular, but the square root of 1, we have no other way to rewrite that. We're just kind of stuck with saying, okay, that's going to simplify back to I itself. Okay, but I squared is probably the most important thing in this list for this course because it shows up a whole lot. So I'm going to put a big old star. I'm going to emphasize that star, make it look super important because you need to remember the fact that I squared is going to simplify to a very convenient number. And that is that I can replace the I with the square root of negative 1. And since I'm squaring that, the squared and the square root are inverse operations, so they kind of cancel each other out. And I can see that I squared is going to simplify to negative 1. Okay, and that is so important. Okay, I'm going to do something a little bit different when I simplify I cubed. So we know that cubing something means I'm going to multiply I times itself 3 times. Okay, and now I'm going to use the associative property of multiplication, right? That means that I can group things that are all being multiplied in different ways, and it's still going to be equivalent. So I'm going to group these first two i's together. Okay, what that's going to do is create an I squared term times I. Okay, and I already have two equivalent forms for these. So I squared, I know the equivalent form is -1. Right, I said that was super important to know. I guess really the equivalent form of I is still just, we know it doesn't simplify, it just stays an I. And -1 times I is going to be -I. So I cubed is going to simplify to -I. Okay, with I to the fourth, I'm going to do something similar. That is the same as I times itself 4 times. And again, I'm going to use that associative property to group two groups of I together. And that's going to change to I squared times I squared, which is going to be the same as -1 times -1. And I know that -1 times -1 is +1. Okay, so we have a nice little pattern that forms here. We end up with I, -1, I, -I, and +1. Okay, let's look what happens when I do this next round of powers of I. So I to the 5th power. Instead of writing it out, I know you know, I to the 5th is I times I times I times I times I. Okay, I'm going to go ahead and use that associative property, and I'm going to group together 4 of the i's. And that just leaves one little I left over that's not in that group. And the reason I grouped it like that is because I know that I to the 4th is 1. And 1 times anything is just itself, right? That's the identity property of multiplication. So I to the 5th is just I. Okay, I'm going to use the associative property for I to the 6th. We end up with, I'm going to group 4 i's together, and I'm going to leave, well, and that leaves 2 i's separate. Okay, well, I know I to the 4th is 1, and most important one to know, I squared is -1. And +1 times -1 is -1. And hopefully you see a little pattern starting to form, is that whenever I can create a group of 4, I'm just going to end up with 1 times that power of I that's left over, and it's going to create the same pattern as that first column of i's there. So I to the 8th, we end up with 1 times 1, which again is +1. So notice I cycle through, let's see if I can't change these. I cycle through that same pattern every single time. There we go, I like that better. Okay. And a really important pattern starts to form with all of those multiples of 4. Every time you have a multiple of 4, you know that that's just going to end up being, we can use the associative property and group them together, and it's going to be 1 times 1 times 1 times 1, as many groups of 4 as I have, and that is always going to simplify down to 1. Okay, so a nice, neat way to remember that pattern, especially to be fast on the ACT, is I won, negatives in the middle. And I would love to do my nice little dance for you. I'll do it in class, but I won, negatives in the middle. It's going to be our chant of the chapter. Okay, so on that note, let's simplify these powers of I quickly. Okay, so I to the 16th power. 16 is a multiple of 4. So I immediately know this simplifies to 1. The answer is 1, but I just want to show you why real quick, right? Okay. So I can create a group of 4 and another group of 4. Remember, all I'm doing is using that associative property. Okay, so I have 4 groups of 4, which is just going to be 1 times 1 times 1 times 1. And again, because 16 is a multiple of 4, I know that this power of I just simplifies to 1. Okay, so what's going to be the challenge is what happens when it's not a multiple of 4. When it's not a multiple of 4, we just need to find what is the closest multiple of 4 without going over. So for I to the 15th, it's going to be I to the 12th, which I know will simplify back to 1. And I have 3 i's left over. So now all I need to remember is what is the third iteration of my pattern of i's. And so that's where I1, negatives in the middle. So I1, I, negative in the middle. So negative I for I cubed. So I know that that is going to simplify to negative I. Okay, 98. Well, I know 100 is a multiple of 4. So if I go 4 back from that, it definitely has to be I to the 96th is going to be a multiple of 4. And that leaves 2 i's left over. So that's going to be 1 times I squared, which is negative 1. So the answer to I to the 98th is just negative 1. Oh my goodness. Okay, if you get to one where you don't know it, right? Maybe this is a multiple of 4, maybe it's not. It's an even number, so I have a 50-50 chance. Let's just real quick divide 4 into it. If you don't remember how to do long division, this is actually a really good chapter for you to practice. Oh, why am I dividing by 2? Because we are going to need to use long division for algebra in the future. And so it's a handy skill for us to review with normal numbers before we start doing it with variables. Oh my gosh, long division with variables, lose your mind. Okay, 4 does not go into 26, so I know that this is not a multiple of 4. So let's see, 6 is going to be the closest. And I have 2/4 left over. Okay, so I'm going to go ahead and move this off. I'm not going to erase it because, again, I told you it's important for us to remember long division. But let's move that out of the way. So I end up with I to the 36th. Oh, no, I'm sorry. That was silly. I to the closest is going to be 144. 36 times 4 is 144. And then I squared. There we go. That adds back up to 146. So I know since 144 was a multiple of 4, it's going to go in one time. I squared is negative 1. So my answer is negative 1. Woohoo! I won. Negatives in the middle. Alrighty, so when we are simplifying radicals in long expressions with like chains of radicals, what's really important is you absolutely must start by pulling out the i's, right? And that's just a phrase that I use. It sounds like I'm pulling out like eyeballs, so that's why I spelled it that way. But you're really just pulling out your imaginary unit, i's, LOL. And I showed you an example of why that is so important and why that matters. Okay, and in these first 3, we can actually get away without having to worry about that because the i's are already pulled out for us. So we can just multiply. We can use the commutative property of multiplication now. So I'm going to be a little bit annoying with this example just to highlight what's happening here. Right? This is all being multiplied. The commutative property says I'm allowed to multiply things in different orders if that makes it easier for me. Okay, and then the associative property says that I can group multiplication. So I end up with 4 times 7 is 28. I times I is I squared. And I know that I squared equals negative 1. So the answer is negative 28. Alrighty. B, okay, notice 2i cubed, the 2i is all in parentheses, so both things are being cubed here. So this is going to be equivalent to 8i cubed times 5i. Okay, I'm going to go ahead and do the associative property and I guess really commutative property and then associative property in my head. So I'm going to go ahead and do 8 times 5 is 40. I cubed times I is going to be I to the 4th. And I know that I to the 4th is just positive 1. So the answer is 40. Okay. Again, I and square root of 3 are in parentheses, so I'm going to go ahead and distribute the exponent to everything in there. End up with I squared times 3. Negative times a negative is a positive. Okay, 3 times 64 is going to be 192. I to the fourth. I know that I to the fourth just equals 1. That's the identity property of multiplication, so I know the answer is just positive 192. Alrighty. D. Okay, again, associative property, we can go ahead and rearrange the groups there, and we end up with a negative times a negative is a positive. 2 times 4 is 8. 8 times 9 is 72. I cubed. We know that I cubed simplifies to negative I. And there that is all simplified. So now on E. E is one where it is so crucial that you start by pulling out the i's. Okay. So instead of just pulling out the i's themselves, I'm also going to go ahead and pull out a perfect square there. So I can go ahead and simplify the negative 9 and square root 2 times 10 doesn't have any perfect square factors. So all I can do is pull out that I, or that imaginary unit there. Okay, and I'm going to go ahead and simplify this now. So I end up with 3i square root 2 times I square root 10, which, using some commutative and associative properties, I end up with 3i squared times the square root. Remember, I can multiply the arguments of square roots, so square root of 20, which we need to be careful because I can actually split up the square root of 20, right? Oh, let me not use red since I used it over there. Square root of 20 is the same as square root of 4 times the square root of 5, which is going to be 2 square root 5. So I'm going to go ahead and multiply this 2 with this 3 now, right? So square root of 20 is going to simplify, and we get 6. Ooh, I squared is negative, so maybe let me write out negative 6 square root 5. Okay, and I don't really love how I showed the work there. I did some side work because I was running out of room. That's an option for you, but I think it's so easy for you to make a mistake if you choose to do your work like that. But this should be the correct answer there. And I can actually verify that with my wrong work that I did. I end up with almost the same answer, but notice in the wrong section, I ended up with positive square root, or 6 square root 5 instead of negative. And that happened because I didn't start by pulling out my i's. Okay, so F, we need to do the same thing. And let's go ahead and start by simplifying first. So negative, oh, why did I put the negative in front? That was silly. Square root of negative 4 times the square root of 6. Square root of negative 1 times the square root of 3. Square root of negative 1 times the square root of 2, right? I broke up all of those and pulled out that imaginary unit. And to go back to my phrase, pulling out the i's, we know that a negative is going to turn into an I. So you could just go ahead and instead of writing negative 1, write an I to begin with. But I end up with 2i square root 6 times I square root 3 times I square root 2. Notice I put that multiplication there for that clear communication. I don't want it to look like the I is underneath the square root with anything in front of it. Okay, I end up with, using commutative property, 2i cubed, and then 6 times 3 is 18. 18 times 2 is 36. I know that I cubed is going to simplify to negative I, and square root of 36 is going to simplify to 6. So putting that all together, we get negative 12i. Okay, and at the beginning of this video, I mentioned that we, now that we know about imaginary numbers, have broadened our number system to now include complex numbers. So complex numbers are any combination of real and imaginary components put together. So standard form for a complex number is going to be a plus bi, where a is just the purely real part of a number, and bi is that imaginary part of the number. And we can actually rewrite any number that we know about now in complex form. So the real number 7, right? 7 is a number that you've known since kindergarten. And we can rewrite 7 as 7 plus 0i. And that shows that while 7 is real, it is also technically a complex number. Just like we can say that 7 is also technically a rational number because I can represent 7 as 7 over 1, right? If I can write something as a fraction using an integer numerator and integer denominator, then it's a rational number, right? So numbers have many different classifications, but this is how I would write a real number in complex form. Okay, a pure imaginary number I can write as there is 0 real part to it, write that 0 component, plus, I already forgot what my number was, 3i. 3i. There we go, and that is in standard complex form. Okay, so just some practice real quick. See if you can rewrite these in standard complex form. And order does matter for standard complex form. Okay, so a, we have 0 minus 6i, or if you wanted to, you could also write plus negative 6i, but you are allowed to use subtraction there. Okay, negative 4, we can rewrite as negative 4 plus 0i, because there is no imaginary component to negative 4. And this looks like it's in complex form, but notice that the real part needs to come first for standard complex form. So 3 minus 2i. There we go. Okay, so we can go ahead and basically combine like terms in this last example, and we just need to make sure that we put our answer in standard complex form. So I'm going to use the associative property of addition here, and you wouldn't normally have to write this out, but I'm going to go ahead and combine my real parts and add that to my imaginary parts, right? Just like multiplication has an associative property and a commutative property, so does addition. 1 plus 9i. B, make sure we subtract both of these components in the second term there. So we end up with 1 plus 5i minus 3 minus a negative 2i. Combine like terms with the real part coming first. Again, subtraction, we just need to make sure we're careful. Minus a negative. 8 minus 8 goes away, so 0 plus 12i. And I know it says standard complex form, but it is absolutely okay. If one of your components is 0, you don't have to write it, and it is still considered to be in standard complex form. I just did it in these two examples up here just to emphasize that these are still considered, like a real number is considered to be a complex number because we can write it with both of those components there. Okay, D, we have some multiplication we need to distribute. That's exciting. So this expression equals negative 15i plus 6i squared. I told you it was going to be so important. Oh my goodness. I squared is the same as -1. Okay, but now I'm not in standard complex form. We need that real part to go first. Woo, we're doing it. We're so excited. Oh my gosh. Okay. Ooh, a nice foiling problem. Okay, so distribute everything here. So -4 minus 8i minus 3i minus 6i squared. Oh my goodness, -4. I'm going to go ahead and combine those like terms. So we end up with -11i. Notice this does not turn into I squared because I'm just saying I have 8 negative i's and I'm taking away 3 more negative i's. So in total, I have 11 negative i's. It's only multiplication that's going to create an I squared term there. And that's just a common mistake I see. Okay, and then plus, oh, let's switch colors. Plus, right, because I squared is -1. And -1 times -6, right, turns it into a +6. I need to go ahead and combine those two real parts. And we just have one example left. F. There's just one little term there. 21 I squared is -21. And we're done. Alrighty. Have fun doing your practice for 3.1. And remember, I won.